Okay, so we have a current flowing clockwise through the solenoid, which means that the solenoid has a magnetic field associated with it that goes into the page. Alright, that's the magnetic field of the solenoid. Alright, so we got to figure out what's going on here. So for part A, it asks, what is the initial direction of the flux through the square loop? Well, using the right-hand rule, if the magnetic flux is into the page due to the solenoid, it's into the page inside the loop. So, okay, now part B, we're told that the current drops to 0. Since the current drops to 0, that means the flux also drops to 0. And so the flux is into the page and decreasing. Okay? Part C, what's the direction of the induced field? Well, the induced field in the square loop is going to try to replace what's being lost. So it's going to be into the page. Right? Now, as far as the magnitude goes, let's see. The magnitude of the induced EMF is equal to n delta phi b over delta t. Now, in this case, what's changing is the magnetic field. So we're going to write delta phi as delta b a cosine theta. Okay, now the initial magnetic field is the magnetic field of a solenoid. That's mu naught Ni over L. And we're given all of this stuff. That's 4 pi times 10 to the minus 7. For mu naught, we're told that the solenoid has 500 turns. And let's see, it has the magnetic flux inside the square, that has an area. Oh, sorry. I'm not doing area yet. I'm doing mu naught Ni over L. So the current is 2.1 amps. Okay? And we divide that by the length of the solenoid, which is 25 centimeters long. Okay, so the initial magnetic field in the solenoid is 0.00529 Tesla. The final magnetic field, if the current drops to 0, is 0. So the induced EMF is n. Now this n is the number of turns in the square, which is 1. Okay, and then we do delta B, which is 0.00529. And it's negative technically, but we're just trying to the magnitude right now anyway, so. Alright, now we do the area of the square, which is 0.022 squared. And then cosine theta. Well, since the square's area vector is lined up with the magnetic field, the external magnetic field, then that cosine theta term is just 1. And we divide by the amount of time it takes for the current to change. Okay, so that results in 1.7 times 10 to the minus 5 volts. It's a lot of n's and a's and so forth to keep straight. You got to understand that this is the n for the solenoid, right? And then this is the n for the square. Right. And then this area is for the square, not the solenoid, because the induced flux, the induced voltage inside the square depends on the area of the square. The field in the square depends on the properties of the solenoid, and that's what we found up here. Okay, anyway, moving on to part E. If the induced EMF is into the page, that corresponds to an induced current that is clockwise. So the induced current is going to go around the square in the same way that the loop does. So it's kind of like inertia. As the loop slows down, the square kind of picks up the slack.